Let me say something about quiz 19. Right after class, I'm gonna post it. It'll be tomorrow at 8 o'clock. I could have posted this over the weekend because you all theoretically have the knowledge to do this, right? It's not like that thing I heard, but you could have done it over the weekend. You can't do it without using your brain on this one. So I will tell you that there's a computation you have to do that's kind of long or whatever, but it's pretty routine. And then after that, I ask you to do some other stuff. My best advice to you is think about what's going on in the problem and don't try to do it directly. Otherwise, you will be burning the effigy out here in the courtyard tomorrow, right? So think about what the question is asking, and there's actually a fairly easy way that you can do this. So it'll be posted after the class today. So what we're going to talk about, this is a theme that we have been on for a bit. And I'm going to expand on this. Linear transformations. And eigenvectors. So suppose B and W are vector spaces over R. So they're just real vector spaces. They might not, strictly speaking, be Rn, because it might be, say, polynomial with degree 3 or less or something like this. Let's say is the basis for B and C M is a basis for vectors. Now, let me kind of draw your picture here. And let's let T B to W be a linear transformation. Okay, so what we have here is now these two vector spaces here are just an n-dimensional and an m-dimensional vector space of the reals. It could be anything, right? Now we know that we can associate this with Rn, so we've got T here. How can we write this as a matrix, right? So suppose I have something like taking the derivative, right? That's a linear transformation from polynomials degree, say 4 to polynomial degree 4. How do I write that as a matrix? Well, I know how to write a linear transformation from Rn to Rm as a matrix, right? I just take the column vectors that the transformation takes from one basis to the other, right? So if this were Rn into Rm, I could write this as some matrix, right? Now I want my matrix to mimic T in some way. Well, how do I do that? Well, I can go back and forth between T and Rn. These are isomorphic. Go back and forth between them by taking, well, if I take a vector V here, how can I associate an element of Rn with it? Well, the idea is through coordinates, right? Because if V lives here, V can be written as, let's say, R1 V1 plus R2 V2 plus Rn V2. Everybody agree with that? Because these B's are a basis for V. So I can write this V, if I just pick out at random a V in here, I can write it as a linear combination of V's, right? What's the most natural thing, given this V, to give me an element of Rn? It's the easiest way that I can take this V, and associate some stack of n elements of R. That's right. Just pull these suckers off. That's what they're for. These R's, given this basis, these are uniquely determined what B is, right? So let's just do that. This is how, and the old-fashioned notation we use for this is the B coordinates for B, right? So these coordinate things, what can I do? How can I mimic this linear transformation by a matrix? Well, I can take whatever B is, and then I can give it its coordinate vector here, right? And how do I decide where to go with this? Well, notice that T of B, it's the same thing as T of R1, B1. Yeah. Right, because that's what B is. And this is a linear transformation, so I can pick this apart for you. And that, my output should be of this form here. And so, if I look at TB, I'm going to write this in C coordinates. This should be what this matrix is in B coordinates. So, what does T do? This goes to TB. TB lives over here. And what this matrix should do is take this to this thing in C coordinates. So this should be in which is, because this is a linear transformation, this is R1 EB1 in C coordinates plus R2 EB2 in C coordinates all the way up to Rn EBN in C coordinates. And this is how you get the matrix. You just see what the linear transformation does and make this do the same thing on the coordinates here. And in fact, I can tell you what this matrix has to look like. This is what does this matrix do? What this matrix does is it takes your input V and B coordinates and turns its output into whatever T to B is in C coordinates. So your matrix here M is T B1 in C coordinates, T B2 in C coordinates, all the way up to T Bn. Now let me just kind of show you that we're in the right ballpark. This thing is in Rn, right? V and B coordinates, because they're in coordinates in B, right? B is an n-dimensional vector space. So a typical element like looks like a stack of these n's right here. And your output is in C coordinates. So this should be an Rm. This should be a stack of numbers m tall. So where should this matrix be that takes Rn to Rm? This should be an invariant matrix, right? And notice that I have n columns, one for each vi, and all the columns are in column. Everybody okay with it? Okay, so this M is called the matrix of P relative to bases B and C. And so here's kind of the diagram here. Your input V goes to P of V. This goes from P to W. This corresponds to whatever V is in V coordinates. You hit this with M. And it turns this to P of V in C coordinates. Right. Let me give you an example. Suppose that we have I'll do a couple of these examples here. Suppose we have T from B to W. And let's write down a couple of bases for this. Let's suppose that T and let's suppose C is so what are the dimensions of my vector spaces then? So V is how many? It's two, so I'm going from the two-dimensional real vector space to four-dimensional. And let's suppose all I have to do really to figure out what I need is to see what that linear transformation does to the basis. So let's suppose T B1 is equal to some linear combination of C's. Let's say C1 plus C2 minus 3C4. And let's suppose the T of B2 is equal to C2 plus C4. So let's find the matrix for T relative to the bases B and C respectively. I'll write this down somewhere here. Well, again, I should have, I guess I should have a 4x2 matrix, shouldn't I? Right, since I'm going from a two-dimensional vector space to a four-dimensional vector space, it needs to be a 4x2 matrix. And this tells me how to build it. The columns should be well, what's TB1 in C coordinates? Well, there's four C coordinates, first, second, third, fourth, right? So what real number, what stack do I have here? In C coordinates, it should be 1, 1, 0, -3. Everybody agree with that? Everybody see how I got that? Okay, tell me, what's then? What are the C coordinates of the second basis element B2?
0, 2, 0, 1.
0, 2, 0, 1. Everybody cool with that? And that's all we need, really. So my matrix M here is, well, you just insert your columns. This should, of course, since it's a matrix, it should be an R, in this case, 4 by 2. So 1, 1, 0 minus 3, 0, 2, 0. Okay. Okay, let's do another one. We'll note first here. Often it's the case that B equals something. Of course, by the way, this can only happen if they have the same dimension, right? Because when you're saying one base is equal, the other have to have the same size. But it's often convenient to have just the basis B and C be the same thing. In this case, right. In this case, sometimes we write this matrix as T sub B if the basis for B and C is the same. Let's look at an example. Let's let here's an alternative R, P3 of X. Let me remind you what this means. These are all polynomials of degree 3 and less, including 0, A0, A1 X plus A2 X squared, A3 cubed. By the way, somebody remind me, what's the dimension of this vector space? 4. 4, right? What's the most convenient basis that you like the most?
1 x squared x.
I like that basis quite a bit because it's kind of easy for me to wrap my hand around. So let's take B. In order. Okay. Okay, so this is going to be kind of a good practice. And here, what I'm going to do is I'm going to let the linear transformations. I want there to be some interpretation here. So I want T of P of X. So when I take one of these polynomials and I insert it to T, we'll take a derivative of this. And we've shown that taking a derivative is linear transformation number of right. Now, I want to get a matrix for this. Now, the matrix that I get is going to depend on the coordinates that I pick. I've already picked, David gave me some rather sagacious coordinates to pick, and so I picked those. But I also need to interpret that in terms of reals, right? So, in this coordinate, so let's go. I'm going to interpret 1 as what are the coordinates of 1 with respect to my basis? One of these, 0 of these, 0 of these, 0 of these, right? So I'm gonna interpret this 1 0 0 0, correct? How do I interpret X in terms of this basis? In terms of R4? None of these, one of these, none of these, none of these, right? X squared. Zero, zero, one of these is 0. And X cubed. 0 0 0 1. Okay. So now what we need to do is find P of R, each of these. So what is P of 1? What's the derivative of 1?
0.
0, right. And writing this in my new coordinates, that one was pretty easy, correct? What is T of X? My second basis element.
1.
1. Which in terms of my basis is 1 0 0 0. Agreed? What is T of X squared?
That's
Right? And what is this in terms of our basis?
0 2 0 2.
Everybody see how we're getting this? And finally, T of X cubed is 3x squared, which is like that.
Wait, why is it 2x and then 3x squared? That's how derivatives work. Oh, no, wait, I thought.
Yeah, I'm taking the derivative, right? So, yeah, I'm taking the derivative, so that's where that part comes from, and then I'm writing it in terms of our basis. Everybody okay with this? Everybody cool with that? Okay, so how do I make this matrix? All right, well, I'll just. For my basis here, B, here. 0 0 0 0, just insert the columns. 1 0 0 0. 0 2 0 0. Everybody okay with that? By the way, what are the eigenvalues of this matrix?
0.
No. All of them are 0. That is correct. Is it diagonalizable? Let's make it diagonalizable. Does everybody agree all the eigenvalues are 0?
Yes.
Okay, so subtract 0 from it. Oh, got the same thing, fine.
Right.
Now, if I were to go through and try to row reduce, I'm not going to do that, but if I was to go through and try to do that, how many pivot columns do I have?
3.
I've got 3. So what's the dimension of my eigenspace for 0?
1.
1, right? You've got 4 eigenvalues. You need a 4-dimensional eigenspace for it to be diagonalizable, right? It's only 1 dimension, so no, this isn't diagonalizable. But I'm gonna square this really fast. 0, 0, 2, 0. And then 0, 0, 0, 6, 0, 0, 0, 0. And then cube this, so I gotta multiply this by this. 0, 0, 0, 6. 0, 0, 0, 0. And you can see this action happening when you take the derivative. If you have, well, let me do it this way, a plus bx plus cx squared plus dx cubed. If you do t once, this becomes d plus 2cx 3d squared x squared. Am I agree with that? And this is basically what's done here. If you do t again, then the total thing is t squared, which becomes 2c plus 6d x, correct? But you put it in 6. If you take another derivative, you get 6d. What happens if you take another derivative? You get 0. Take 4 derivatives depending on them and go through, let's get 0. And you can see this matrix, the powers of it are basically taking more and more derivatives and finally gets crushed out to 0. Everybody okay with this? Okay, any questions thus far? Questions? Okay, so I'm going to give you a theorem, and this theorem actually generalizes this business that we were talking about when we talked about diagonalization last time. And then I'm going to work out an example where we can kind of see this in action. Theorem. Suppose we have A equal P, B, P inverse. Where P is invertible. I guess that's kind of obvious since I did write a P inverse right there, but let's make it clear P is invertible. If B is the basis for Rn formed by the column of P, by the way, before I continue, let me take them on the side here. Here we're talking about n by n matrices, all my players, n by n matrices. If B is the basis for Rn formed by columns of P, how do I know the columns of P form the basis for Rn? Very good. There's n columns, so I've got n things, and they're linearly independent. In Rn, if you have n linearly independent things, they're automatically a basis, right? So, okay, this statement is not totally out in left field, makes sense. So, I just look at the columns of P. Since it's a verbal, I know that those columns form a basis for Rn. And this really, I love this theorem because it kind of allows you to kind of cherry pick. Then B is the matrix. For let me emphasize it. That is the matrix with respect to the basis B here. For linear transformation. Defined by Px equals X. So this matrix here, which is PVP inverse, whatever this matrix is, it defines a linear transformation, right? I can multiply by any matrix. If X is an element of Rn, a multiplication by any matrix makes a linear transformation. If A is PVP inverse, then what this means is the columns of P, then B is the matrix for this transformation right here. So let's see what's true. I think this is really one case where we can kind of do the computation and the proof to see why this works. So let's let B1, B2, Bn, B basis. B column P. And so let me also point out that this is our base. We know that P is invertible, so this indeed, these columns do form the basis for our ends. So the matrix P, since it's the columns, looks like this. So what it looks like is going to be useful in a moment. There we go. P just looks like that because we just cherry picked out the column B. So P X X B. So whatever X is, put it into B coordinates, and P changes. When you multiply P times X and B coordinates, it changes it just to X. Remember what this is P is matrix. Because the columns of P are the coordinates of B, right? It's the basis of B, coordinates of B. So the columns of this matrix are B coordinates. So when I multiply P times X and B coordinates, it changes it to standard, right? For example, 1, 0, 0, 0, 0 turns into the first column, 1, 0, 0, 0 turns into the second column, and so forth. So really what this does is this gives X back. This is X and B coordinates. Matrix. X and B coordinates to standard. Y'all remember when we did all that? Right? And so I'm going to use this observation to get what I want here. And of course, P inverse is the matrix that changed standard back into B coordinates, right? Basically, all these are multiplied on the left by P inverse here. XB is P inverse of X. So if we have the linear transformation, I want to show that this, I get the appropriate matrix here. So if we have the transformation that T times X is A times X, I want to show that B is the B basis matrix for this. then TB is the matrix given by TB1 and B coordinates. TB2 and B coordinates all the way up to TBN and B coordinates. Right, this is just a matrix that does what I want to do, take B, etc. So let's massage this. TX is AX, so this is AB1 and B coordinates. AB2 in B coordinates, all the way up to ABN B coordinates. Because the transformation to B1 is just multiplication by that vector. And so notice that if you have Fred in B coordinates, that's P inverse of Fred. So this should be here I have Fred, it's AB1 in B coordinates. That should be B inverse without the P. So this should be P inverse AB1, P inverse AB2, P inverse ABN. So it should be these columns right here. Everybody okay so far? Now notice I use this term really kind of loosely, common factor. Notice there's a P inverse A in front of everything, right? And so I can write this as P inverse A B1, B2. This right here is a matrix, right? This thing here, right? What's another name for this matrix? It is P. So let's kind of go back to where we were here. So what we have kind of to wrap this up is so TB, the matrix we started off for here actually turns out to be and P inverse AP is B. Because remember in the theorem, we had that we assumed that A is P, B inverse. And so P inverse AP is equal to B. So this gives us exactly what we wanted. That is, the transformation matrix is exactly B. Okay. Any questions on that? Let me show you this kind of coordinate change for the concrete example here. Let's start off. And maybe you'll see the practicality for this. So let me give you kind of a simple 3x3 matrix. Let A equal 5, -3, -2, 4, -2, -2, and 2 minus 2, 0. Right? Okay. And my instructions on this problem are By the way, not every matrix is represented by not every transformation. Not every matrix is diagonalizable, so not every transformation can be realized as being represented by a diagonal matrix, right? So along the way, hopefully we'll figure out that it works for this one. And by the way, nobody wants to multiply this matrix out, right? I mean, if you have to do a lot of work, maybe this transformation is important, like doing some kind of computer graphics thing, right? You're fixing signals or, doing some kind of image adjustment or whatever. You don't want to do a zillion computations for this, even 3 by 3, right? I mean, it's awful, right? So you might want to look and sniff around and see if there's a better basis, right? A basis where this transformation is much easier, right? Certainly not the standard, right? The standard, this is what it looks like in standard, it's a mess. So what do we do? Well, first thing we do is let's find the eigenvalues and then the eigenvectors. So first I'm going to find the characteristic polynomial by taking the determinant 5 minus x minus 3 minus 2, 4 minus 2 minus x minus 2, 2 minus 2 minus x. Everybody cool with that? So what do I get? This is 5 minus x times the determinant of this guy. So it's going to be x squared plus 2x. That's it for you. Minus 4. Okay, this is 3 plus 3. Remember, you switch the sign here. Times the determinant of this mess here in the middle. So it's going to be minus 4x. And it's going to be plus 4. And finally, this guy, which is negative 2. Times the determinant of this. That is going to be minus 8 plus 4. So it's going to be minus 4. And that's going to be 2x. Now we'll see what I get. Let me multiply this mess out here. I get minus x cubed. I get minus 2x squared plus 5x squared is 3x squared. I get 4x and 10x is 14x. And I get minus 20. And I get minus 12x plus 12 minus 4x plus 8. Which equals minus x cubed plus 3x squared. 14 minus 12 is 2. Minus 4 is negative 2. And then I get minus 20 plus 20 is 0. Is this matrix invertible? Is the matrix A invertible? What's one eigenvalue that jumps right out at you? 0. Let me ask again, is the matrix invertible?
No.
No, because the product of the eigenvalues is determined, so it says that determinant of 0. This is minus x times x squared minus 3x plus 2, which is minus x times x minus 1 and x minus 2. So in fact, the eigenvalues I get here. Or 0, 1, and 2. Everybody okay with it? Okay. Is this matrix diagonalizable? Anybody, so this is 3 by 3 matrix. What do I need for a 3 by 3 to be diagonalizable? What's that number 3? You have to have 3, that's right. Let me just say this a little bit more carefully. You have to have 3 linearly independent eigenvectors, right? That's what has to happen. The problem with using eigenspace is if you have 2 different eigenvalues, then put it together, that doesn't make an eigenspace anymore. Do I get 3 linearly independent eigenvectors here? I've got a guarantee from God on this one. Somebody tell me why? I've got 3 different real eigenvalues. So remember, if you have different eigenvalues, you have to have linearly independent eigenvectors. So I'll win on this one. It's going to be diagonalizable. Everybody follow that so far? So eigenvectors. I want to run the test on this, so I will trust that you all can find the eigenvectors. And I did this, and what I got was for lambda equals 0, I got one linearly independent eigenvector, and I got 1, 1, 1. Try to do this yourself on the matrix and make sure you can get the eigenvectors, but here's what I got. For lambda equals 1, I got 102. And for lambda equals 2, I got something else. What did I get? 110. So if I can fill some of this in for you. I'm going to put on P and bar, yeah, because I've got to figure out what it is. But can somebody tell me how to find the P? Okay, how about the D? Well, eigenvalues on the diagram. Give me some order. I don't care what order you give me.
That's 0, 1, 2.
Okay, how about that? That works. 0 eigenvalue, put in its eigenvector. 1 eigenvalue, put in its eigenvector. And 2 eigenvectors. There we go. There's your P. You can figure out P inverse, right? Everybody can do that. And so what's the basis? So the basis is determined by that P. And in fact, the basis is the eigenvectors. And this is why it works. And this is why eigenvectors are magic, right? So if you look at A, well, whatever A was, minus 5 or 5 minus 3 minus 2, 4 minus 2 minus 2, 2 minus 2, 0, I think. What happens when what do I get for A times? What happens when I multiply the matrix 8 times 1, 1, 1? That just means basically add everything up. So the first coordinate I get should be 0. And I add up everything in the second column, I get 0. at the zero. So this is 0 times 1.1. Everybody agree? Translation of this is AX is just 0 lambda X, right? And so this is 1, 0, 0 in C coordinate or in B coordinates is 0 times 1, 0, 0 in C coordinates. If you look at A times 102, this becomes 102, that's going to be 5, 0, that's going to be 1, 1, which is 4, minus 4 is 0, and 2. So A times 102 gives you 102. So translation, A times 0, 1, 0 in C coordinates is the same vector 0, 1, 0. Everybody agree with that? So it takes, not C coordinates, I keep saying that, B coordinates, to 0, 1, 0 and B coordinates. And finally, if you look at the last one, which is 1, 1, 0, this becomes 2, 2, 0, which is 2 times 1, 1, 0. So A in 0, 0, 1, B coordinates is 2 times 0, 0, 1 in B coordinates. So the matrix for A in C coordinate or B coordinates is exactly this matrix here. Everybody see that all right? Okay, so look that over. If there's any questions, let me know. My office hours have to end a little bit before 1 today because I've got one of those off meetings. So let me know that after class if you need to see you then. Otherwise, we'll see you guys on Wednesday. I can post very soon.